Thank you, Björn, for the kind words, and thanks to the organizers for organizing this really great forum. It's been a pleasure to attend all of these talks. What I now like to talk about are unsupervised methods for learning regularities, for learning structure out of images. We're going to see that a primary tool to actually achieving that goal are compositional grouping approaches, which then enable us really to tackle this problem without having any labels provided. I was told that the audience is pretty diverse and background is also similarly diverse, so that I should give a little bit of background, which I surely love to give, and to sort of embed that a little bit with respect to the previous talks. It's probably best to sort of link that to Frederick's talk, who said that he wanted to go about part learning without actually having labels for the parts or being told what these parts actually are. We want to go one step further. You remember you said he utilized like millions of ImageNet images, millions of images from Places data set and Pascal and so on. We're having no such labels provided at all. We just provided with the images. The underlying rationale is obviously that downloading images from the internet or from where else is cheap, but getting labels for them is a costly endeavor. Now, there's another goal for doing that as well, and that is that humans have always been actually sort of striving for finding structure and regularity out in our world, and the world surrounding them, maybe even with their own body, trying to figure out about regularities, and then the opposite as well, abnormalities, where sort of the similarity and regularity structures are actually broken. It's not just been in the here and now that we've been looking at structure, but also if you go to totally different temporal and length scales as well. People have been looking out in the stars, as you know, and trying there to figure out about patterns, about repeated similar structures, linking that to patterns that we have in here in our world. For instance, the placement of the sun and other stars with respect to the seasons of the year, and then making obviously predictions about the future from that. It's not just been observing what human beings have been doing, but also really acting upon that, trying to utilize our sense of structure and regularity and superimposing that on the world in agricultural processes, in art as well as a lot of others, where a sense of beauty, or be it just like mastery of the world around us, has been superimposed to actually make it structured and regular. And if that's not enough, we've been just utilizing it to merely simplify our whereabouts in this world, or probably just for lack of creativity, as you can also see here, turning special moments in something which is probably much less special if you see it in the greater context. Graduation ceremonies or wedding ceremonies. If you look at the greater context of other people doing the same, you here in these average images can see that there's probably not so much speciality there. And art for sure has also put this sort of into kind of the extreme, like was Verdi here, who took ordinary images and then tried to sort of go with this ordering to such an extreme that you could call it almost an IKEA world, where things are really enumerated and you see this structure. Now, where does this striving for structure come from? I would argue it's deeply rooted in the world around us, because regardless if you take a microscope, your bare eyes, or a telescope, on all sorts of scales, there's a large degree of structure and regularity out there, and people have obviously been observing that and then been fascinated with that and trying to figure out like what this structure is, to understand the world better, to learn from these repeated structures. And that's in essence what pattern recognition machine learning is also all about, right? We look at images, for instance, that we had in the past, to extract repeated structures, to then learn about occurrences in the future, so that you can walk into such a room and reason about this thing here being a chair without probably even attaching a label to it. You've just seen similar things in the past and then know how to act upon them in the future. But it's not just machine learning that has been looking, for instance, at images. and then extracting these patterns out of them. There's a broader theme there. It's actually very much related to the scientific method, because one can definitely argue that the structure of the world is actually the essence for science working overall. And so the scientific method has been around for a long time. If you, for instance, look at these periodic tables going back to Mendeleev's thinking like 150 years ago, where he was able to figure out about regularities in the elements that actually fundamentally make up this world, and then being able to predict elements that nobody knew at that time. Why? Because there is a certain amount of regularity, which for the first time really enabled us to, on a very fundamental level, think about the world and make predictions that nobody could do beforehand. It's not been limited to just physical elements, also to living beings, plants, and so on. Thinking about similarity has inspired people to group species accordingly, bring these similarities into context. And then there's obviously the ultimate goal that people have always been sort of trying to address, and that is nothing less but organizing the whole knowledge of the world into an encyclopedia. These days you would probably go for Wikipedia or something like that. We know it's a never-ending endeavor. New knowledge comes in every day, and nevertheless, like this ordering of all the things in the world based on their similarity has been really sort of inspiring people to actually go for. Now, I would argue that there are different ways to actually bring order to our world, to actually extract similarity relationships between entities, figure out about their relations. And the oldest of all is definitely rooted in Aristotle's thinking, Plato's thinking. He had this nice exposition on categoriae, where he was actually arguing that there are certain principles, certain properties, necessary and sufficient properties, that you can attach to all members of what he then called a category, or in Latin, these predicamenta, certain necessary and sufficient conditions which all members of a category actually obey. And as you can see, this is very much sort of the root of our scientific thinking, that we have certain axioms which you can formulate, and then you can check them for each member and can ask, does that actually fall into that category or not? So this is very basic, and we are utilizing that every day. But in the 1970s, psychologists thought a little bit further about that, and they noted that their subjects, human observers, when observing scenes, they were not, when thinking about birds, for instance, coming up with a set of axioms to say, like, this is a bird or this is a car. Rather, they saw that their subjects actually came up with prototypical representations for a certain category. So if you ask 100 people, like, what is a bird? They would probably come up with a rendering, at least in their head, or even draw it on a piece of paper, which looks a bit like a blackbird, for instance, or a sparrow. But you see it much less likely that somebody would come up with a penguin, for instance, right? I mean, this is somewhat an outlier. So they figured out that people typically prefer an average representation. So if you can, you try to average all of the samples of a category in this average representation, and that's what people actually were striving for. So it has an additional effect, and that is that these categories started to be fuzzy at their boundaries. You have this average representation, which is kind of a centroid or prototype, if you think of the analogies to clustering. And at the boundaries, things actually get a little bit more fuzzy. However, this prototype theory has problems with large amounts of intra-class variability. And so a few years later, there was an opposing stream in psychology called exemplar theory, which actually advocated sort of not going for a single average representation of a category, but rather than that, going for a lot of individual exemplars. So to speak, you go for all of these extreme cases, memorize them, a little bit like a nearest neighbor classifier, and at any rate, you try to avoid a single generic abstraction of a category. Over recent years, these exemplar models have become very popular in computer vision. Why? Well, we started off with categorical models, where we try to put all the samples of a category into a single classifier. But it turns out that modeling all of this intra-class variability by a single classifier is a pretty tricky thing to do. And that's why exemplar support vector machines and other exemplar approaches became very popular, where you just take a single positive, lots of negatives, train a discriminative classifier and utilize that for all sorts of tasks like recognition, grouping problems, segmentation, and so on. Again, we simplify these complex models by splitting them up into a lot of simpler models with less intra-class variability. So now we have these different theories. And if one takes a closer look at these definitional rule-based approaches, prototype theory and exemplar theory, you observe that all of them have their benefits and their shortcomings, right? In one way or another, we would prefer this single compact representation of a category and not store all of the individual samples. At the same time, we would like to have a nice discriminative approach which can actually also say like how to discriminate these classes. We would also have this synthetic aspect that we can generate new samples for a category, and surely we want this thing to be data driven. We can't say to a machine, to a computer, okay, think about the world and come up with what makes, I don't know, up birds, for instance. So we seek a data driven approach, much like these bottom up approaches, not so much this analytical approach at the top. So the question is really, how can you get the best of all of these three worlds? And it turns out that for a lot of tasks, a lot of important tasks that we, for instance, have in computer vision machine learning, such as categorization, object classification, you can formulate them in a way that they become a simple grouping problem based on some sort of similarity. And the problem is then obviously just deferred. You need to learn similarities. Similarities which in the top approach there, rule-based approach, would be defined on predefined characteristics based on a central normative prototype and prototype theory, or based on a lot of individual exemplars. Now, learning similarities has been a central problem of machine learning, where you can go for bilinear forms, for instance, or you can go for an embedding, and then in this embedded feature space you can just utilize Euclidean distances or something like that, embedded in such a way that similar samples end up being close by and others further away. Similarity learning, especially in recent years with deep learning coming around, have been tackled in a supervised manner. And there's been three broad streams in which you can categorize almost all of the work there. Classification approaches, trying to learn similarities in a regression sense, or obviously ranking problems where you sort samples but you don't care about their actual similarity. With deep learning approaches, there has been a recent sort of push in the direction of learning similarities with two-stream architectures, CMEs architectures, where you take two samples and then directly learn whether they're similar or not, and also deep ranking approaches and the like. But I would argue that a problem with many of these CNN-based approaches to learning similarities has actually been that you really have this end-to-end learning, like Thomas was talking about earlier on, that this requires actually strong supervision, a lot of training labels. And as we've seen, images are cheap, but getting labels for them is quite costly, especially if you need labels for parts or things like that. And there's been a recent stream in the field to avoid at least this pre-training on large data sets, but even approaches like this here from Gupta's group, which just recently came around, even that approach then eventually relied upon some fine-tuning on a larger data set like Pascal, for instance. So what we want to do is we want to avoid all of these labels and just take the images. Now, I said there's another sort of set of approaches for learning similarities, and that are these two-stream architectures where you take two patches, for instance, or two images, and then directly learn if these are similar or if they are not similar. But since you're in this tuple space, you have quite a high complexity. Typically, it's quadratic in the number of dimensions, and that then eventually requires a lot of training samples and therefore requires a lot of time. In this ICCV submission from Ayosha's group from last year, they reported a training time of several weeks. which is pretty costly. So we ask ourselves, can we do that more efficiently? Can we turn this complex pairwise problem here into a much simpler classification problem? So rather than directly learning if two patches are similar, can we just classify them, attach a label to them, and then hope that similar samples end up having the same label? Now you might directly object. He said, like, we are not having any labels. Correct. We're not having any labels. So the problem is, can't we automatically come up with this classification problem without being provided with the labels in the first place, so that eventually samples which are similar get the same label? In that case, we would not have this complex problem here, and we would implicitly learn a representation, an embedding, which then mitigates the similarities between samples. Now, an approach to actually learn such a classification problem without labels is obviously the exemplar-based approach. There you just need a single positive, lots of negatives we can always have, but just a single positive. For a single positive, you don't need a label, right? It's just a single positive. However, the problem with exemplar-based approaches is that you're having your single positive, you're having lots of negatives here, but you cannot model the intra-class variance of the positive class. You don't know if it looks something like this, this, or this, and that's what you're truly interested in. You want to know what the birds look like, not just what separates this one exemplary bird from all of the other animals. And you want to have a model for this positive class, but you're not provided with that. There's been recent work on synthetic augmentation, but even that sort of provides you with a problem, because you beforehand have to model the invariances and then superimpose them, but that's not the full invariance properties that you have in all of your data. Secondly, with just a single positive in exemplars, you have a high imbalance between your positive and your negative classes. So if you do stochastic gradient descent when training a support vector machine, it heavily gets biased towards the negatives, which you obviously don't want to have. And lastly, if you do SGD, then such a batch contains not just a single exemplar, right? You need to train that on a lot of data. So there's a high likelihood that you have several exemplar classifiers, this green one here and the blue one, and these samples, the green and the blue sample, they are actually very much the same. So in your SGD training, however, you then also try to separate between the blue and the green sample, although they are the same, so you will have a lot of training relationships that you should not actually train against another. So in short, what we seek is we want to move away from the single exemplar and want to gain a composition of samples, so that we're not just having the single poster here, for instance, but a lot of related posters, but they should be all mutually related, not just to the single exemplar that you're starting with. So let me just summarize the setting here. We want to do an unsupervised deep learning of similarities, no labels provided, and we want to utilize that to really learn fine-grained similarities. So consider, for instance, the problem of learning similarity between posters and saying these posters here are the same, these are different, and so on. Or you have a gait cycle where you would even say that different posters during or in the course of the gait cycle are similar and dissimilar. Olympic sports data set, UCF sports, and so on. These are data sets that we are first of all considering before coming to other problems like Pascal as well. Now the problem when dealing with this problem is that if you take an arbitrary similarity measure, you might have a few similarities which are reliable. You might have a few dissimilarities where you say like, okay, these are definitely dissimilar. But the majority of samples show some mediocre similarities. We neither know if they're similar nor if they're dissimilar. They're somewhere in between. You cannot rely on these similarities. And if you look at the full similarity matrix, this here would be a long jump action, so the person is actually accelerating. You see a lot of off-diagonal lines here coming from sort of the repeated gait cycles, but there's a lot of sort of blurry structure in between which we want to get rid of. So we want to move from the single positive to several positives, but it's really uncertain. We really don't know how to get that, because if you would utilize all of the similarity matrix here for initializing your algorithm, you would have a lot of corrupted similarities which actually hurt you. So in short, a problem is if I take a single exemplar here, I might find a few nearest neighbors, but these nearest neighbors towards another don't obey transitivity relationships and so on. Yeah? This might be similar, but these here might be partially similar, partially dissimilar. If you throw all of that together in SGD batch, your model says like, yeah, that should be similar, but that should be not similar. And then you train it and train it and training, and your SGD pushes that in this direction and that direction and doesn't know where to go. So we follow therefore an approach which utilizes only the most reliable similarities and dissimilarities. The rest we disregard, and then we hope that in the course of training a CNN, we can impute labels in between here, retrain the model, and then get better similarities. But for doing that, we need compositions of mutually related samples, where we can say like all of them can go into the same batch of SGD training, and they are all okay if they get the same label. And at the same time, we also need dissimilarity relationships. It's not just okay to say, okay, these should be similar, but we need dissimilarities as well. So we need to assemble batches of compositions which are mutually dissimilar. Then we have similarity relationships and dissimilarities, and we can eventually train a standard convolutional neural network, whatever that should be, AlexNet or VGG, GoogleNet, and so on. Get a representation, an embedding as we've seen it beforehand, and with this embedding we then get new similarities which we can utilize then to continue with that approach. So one way to get compact compositions would be a simple initialization using complete linkage algorithm, which then assigns exemplars here to different compositions. Several exemplars can go, or an exemplar can go into several compositions, so these compositions might be having mutual overlap, and if they have mutual overlap, it's clear that they cannot go into the same SGD batch, because some of them are similar, others are dissimilar, but they have the same label. That ain't gonna work out. So we seek a partitioning of our data where all compositions in a single batch for training the model, they're all mutually dissimilar. And at the same time, that's not it. At the same time, we want with these individual batches to maximize the coverage of our data. So as to make sure that within very few iterations, we actually get we will actually have seen all of the data that we have available. More data obviously helps us. So here in different colors, you can see different partitions which would go in the first batch, second batch, third batch, and you can see that within one batch, all of the different compositions which you see here are mutually maximally far apart. So at the end of the day, we partition this complicated problem of learning all of these similarities, where we have similarity relationships which might be uncertain. We partition that over several simpler problems, and it's a little bit like juggling. You make sure that things which might actually collide with another end up in different batches, and then you juggle from one to the next, iterate back and forth, and your CNN actually then balances all of these relationships. After getting these compact compositions, we then optimize this batch formation by making sure that all of the cliques in the same batch are mutually far away from another. The cliques themselves are compact. We maximize the coverage that each individual batch gives us. And if you go over all of the individual batches, all batches together, they should obviously contain all of your training samples so that you don't miss a single valuable training sample. This joint optimization here gives you a single data matrix which assigns compositions to batches, and again, a single composition can go into multiple batches, but you make sure that all compositions in the same batch are dissimilar. So you have within a batch reliable similarity and dissimilarity constraints, which we can utilize for training, and then in a totally unsupervised manner, you can learn similarities of postures, for instance. Yeah? So you take an individual posture and then ask the algorithm what are similar postures, again, without actually having been provided with any labels here. I can compare that on the Olympic sports data set, and yeah, sure you get some better performance with that. What you can also do is take a query and then average over the nearest neighbors to get an essence of like how nice these nearest neighbors actually match. And it's probably somewhat difficult here on the projection to see, but with this compositional grouping, you get pretty nicely the posture here actually captured, whereas taking standard LXNet or HOC LDA gives you a pretty fuzzy representation. People lose their legs, parts of the torso and so on, they're lost. Or if you look at the similarity matrices, the approach itself, you can nicely see these off-diagonal structures. You can even see how they're converging because the person is accelerating, so time is running in that direction here. So a person is accelerating, they're getting closer and closer. Whereas if you just take a single exemplar and train a support vector machine, or you just take the k-nearest neighbors, but not a compact composition, it's all getting pretty much fuzzy. You can go across data sets, take samples from one data set and then ask for each of them what are similar postures. You see this is going across sports, it's just asking what is a similar posture, because there's no labels provided. And you can evaluate that on annotated key points during testing. Sure, if you have labels provided, you can go much further, but this is just to advocate how far you can actually go in unsupervised manner. I can show this on a video here, where for each individual frame, nearest neighbors have been utilized to then come up with this rendering here. And just sort of capturing the similarity structure and disregarding everything that the approach eventually did not care about. You see that during jumping, obviously, there's a lot of different postures, so finding neighbors. There are just not enough nearest neighbors in the data set to find this prototypical or these related postures. And finally, I want to show one example of extending that beyond postures to a standard problem of object categorization. Pascal we've seen beforehand. And in this case, we're totally unsupervised. Yeah, we're not utilizing any labels. As I said beforehand, Frederick utilized the ImageNet, millions of ImageNet images with labeled places, and then Pascal. We're not utilizing any of these labels. We're just provided with the Pascal images and then trying to make sense out of these images to learn what really makes up, I don't know, a bus or a motorcycle or something like that, learning similarities in a totally unsupervised manner, proposing the nearest neighbors, and then you can ask, are the nearest neighbors on your test set actually having similar labels or not, to come up with classification performances. We're comparing here against this very recent paper from Wang and Gupta, who also started off with an unsupervised approach. However, they utilized additional data, video data, for training their approach. And if you sort of put that on top of that, you obviously get significant extra performance. With additional labels, obviously, like RCNN, you're obviously still better. So, let me conclude. We've looked at a totally unsupervised approach for learning regularities in large data sets, for learning similarities, for instance, between postures or object classes. The way to actually go there has been exemplar-based framework, because in that case, you just start off with a single sample and its similarities, but you don't need any labels. This we have utilized to take standard CNNs, which are typically trained in an end-to-end, fully supervised manner, to turn them into an unsupervised classification approach. The costly pairwise scenario that has been common for learning similarities in CMEs or two-stream architectures has been avoided by just turning that into a simple classification problem where the labels are automatically obtained. And these exemplar compositions, together with this batch formation to get the negatives, do three things for us. They reconcile the different exemplars with respect to another, so that transitivity relationships are actually met, which beforehand were actually hurting, that certain samples said they're similar and others said they're dissimilar, and we could not get these similarity matrices together. We can now much better model intra-class variability than just with a single exemplar. And finally, it actually helps us to handle this large imbalance between positives and negatives. So with that, let me thank you for your attention. I'm happy to answer any questions.